Hello everyone. A warm welcome to my channel Physics for Engineers. I am Dr. Thirumalrao Gurugubelli, Associate Professor and Head, Department of Basic Sciences, School of Sciences and Humanities, SR University, Warangal, Telangana, India. In this video, we will discuss about the extrinsic semiconductors. Up to this point, we have discussed intrinsic semiconductors, which are pure semiconductors. However, the intrinsic semiconductors have a major limitation, that is, their conductivity is relatively low. To make the semiconductors more useful in practical electronic devices, the scientists developed a technique called doping. Doping is the process of introduction of impurity elements into the pure semiconductors. A small amount of impurity atoms into a pure semiconductor crystal will change a significant change in the properties. The resulting materials is known as extrinsic semiconductors. The word extrinsic simply means that it, its properties are influenced by an external factor, namely the impurity atoms. An interesting fact that even one impurity atom among millions of silicon atoms can significantly change the electrical conductivity. As like one drop of curd will change the complete structure of a full part of milk. Similarly, the one doping element can change the entire semiconductor properties. The purpose of doping is to increase the number of charge carriers and to improve the mobility of charge carriers. Depending on the type of impurity added, we can classify the extrinsic semiconductors into two categories, namely N-type semiconductors and P-type semiconductors. In N-type semiconductors, the electron becomes more and the majority charge carriers are electrons. In p-type semiconductors, the holes became more, means the holes are the majority charge carriers and electrons are the minority charge carriers in p-type semiconductor. This ability to control the charge carriers is what makes semiconductors so valuable. Think of intrinsic semiconductors like silicon as a small village road with limited traffic. By doping, we create the additional pathway allowing more vehicles or in this case charge carriers to move through the material. Virtually every electronic device around us uses an extrinsic semiconductor. It may be a smartphone, laptop, or LED, anything. Every electronic device which is having a number of transistors and diodes which are made up of extrinsic semiconductors. Without doping, the modern transistors, integrated circuits, microprocessors, LEDs and solar cells would not exist. Therefore, doping is one of the most important concepts in semiconductor physics and electronic engineering. Let us first discuss about the n-type semiconductors. An n-type semiconductor is formed by adding a pentavalent impurity to the pure silicon crystal or germanium crystal. The pentavalent means the impurity atom possesses 5 valency electrons in the outermost orbital. Common pentavalent dopants includes phosphor, arsenic, antimony. Now let us understand what happens when phosphor is added to the silicon. Silicon has 4 valency electrons and forms 4 covalent bonds with the neighboring atoms. A phosphorus atom has 5 valency electrons. When we dope the phosphor into the silicon, out of these 5 valency electrons, 4 electrons participate in bonding with the neighboring silicon atoms. However, the 5th electron remains weakly bound. Only a very small amount of energy is required to release its extra electron. Consequently, a large number of free electrons became available for conduction. Since electrons are dominant charge carriers, then the material is called n-type semiconductor. The latter, n stands for negative because electrons carry the negative charge. It is important to remember that the semiconductor remains electrically neutral overall. The number of positive charges still equal the number of negative charges. Only the carrier concentration changes. Because n-type semiconductor contains many free electrons, their conductivity becomes much higher than that of the intrinsic semiconductor. This principle is widely used in transistor fabrication, integrated circuit design, and high-speed electronic devices fabrication. Let us examine the carrier distribution inside an n-type semiconductor. You can see here in the diagram, initially one electron, the excessive electron is came out of the bonding with a small energy, and that strikes the another electron while it is moving freely throughout the semiconductor. Then that disturbs the another bonding. Another electron is released from the bonding by creating a hole which is marked with red space. Later, that hole attracts the another nearest electron to that place. Then the hole is shifting to the other place. So similar way, the process will be continued and more number of electrons and holes will be generated in the semiconductor lattice. After doping with the pentavalent impurity, the free electron became abundant, and these electrons are called majority charge carriers because they exist in very large number. Holes still exist due to the thermal generation, but their concentration is extremely small. That's why the holes are called as minority charge carriers in n-type semiconductor. A simple way to remember this is the majority charge carriers dominate the conduction. Minority carriers exist but contributes less. So when an electric field is applied, the abundant field free electrons moves rapidly towards the positive terminal. This movement produces a substantial electric current. Because the number of free electrons is much larger than the number of than the intrinsic semiconductors, the conductivity increases dramatically. An analogy would be a highway with thousands of vehicles moving efficiently compared to a village road. Even the village road having very few vehicles, the highway has thousands of vehicles. The movement of vehicles on the highway is very efficient and it is much better than the village road with only few vehicles. In particular, the electronic device controlling majority and minority charge carriers is crucial. The operation of diodes, transistors, and integrated circuits depends heavily on the carrier concentration and movement of charge carriers. Thus, understanding n-type semiconductor is the first step towards understanding the semiconductor devices operation. Now let us see the second category of extrinsic semiconductors, that is p-type semiconductors. A p-type semiconductor is created by adding a trivalent impurity to the pure silicon or germanium atom. Commonly the trivalent dopants including aluminum, gallium, indium, and so on. These atoms possess only 3 valency electrons. When a trivalent atom replaces a silicon or a germanium in the crystal, it can form only 3 covalent bonds. One bond remains incomplete because the impurity atom lacks of the 4th electron. This deficiency creates a hole. As a result, a large number of holes are introduced into the crystal. Since hole becomes the dominant charge carriers, the semiconductor is called as p-type semiconductor. The letter P stands for positive because the holes behaves as a positive charge carrier. Just like n-type semiconductor, the crystal remains electrically neutral overall. The key difference is that Holes now dominate the conduction instead of electrons. P-type semiconductor are equally important in electronics. When P-type and N-type materials are joined together, they form a PN junction, and based on this PN junction, the diodes are developed. So the PN junction formation is the foundation of the diode fabrication, are transistors, LEDs, solar cells, and many other devices. Hence, understanding the p-type semiconductors is also essential because it is also equally dominant materials in semiconductor devices. Let us now focus on the charge transport in p-type semiconductors. Because of trivalent doping, large number of holes are created. These holes become the majority carriers, and electrons generated thermally are present in much smaller number, and therefore the electrons become minority charge carriers in p-type semiconductors. When a voltage is applied, holes moves towards the negative terminal. Although holes are not physical particles, their movement can be treated as a positive charge transport. This greatly simplifies the semiconductor analysis. You can see in the diagram the whole movement. So you can imagine a row of seats where one seat is empty. As students continuously shift to occupy the empty seat, the vacancy appears to move along the row. Similarly, more holes appear to move throughout the crystal structure. The movement of these holes consisted electrical current. Since holes concentration is very high in p-type semiconductors, the conductivity is significantly greater than that of intrinsic semiconductors. This carrier transport mechanism becomes extremely important when analyzing the PN junction and transistor operations. So understanding both N-type and P-type semiconductors allows us to appreciate how semiconductor devices control the current flow with remarkable precision. So now you can see here how the charge carriers are moving. Initially, if you see, the only hole is present near the element B at the middle. That attracts the next neighboring electron, and the hole is shifted to that place. And the hole is attracting the next neighboring electron, and the hole is shifting, like as mentioned, the students occupying the empty seat. The empty seat is like moving away. The similar way, the electrons and holes are transporting in two opposite directions. Electrons are moving in one direction, the hole is moving in the opposite direction. So have already we discussed about the n-type and p-type semiconductors separately. Let us now summarize the current flow in extrinsic semiconductors. The extrinsic semiconductors contains two types of carriers: majority charge carriers and minority charge carriers. In p-type semiconductor, the holes are majority charge carriers and electrons are minority charge carriers. Whereas in n-type semiconductor, the electrons are majority charge carriers and holes are the minority charge carriers. These majority charge carriers depends on the type of doping. When external electric field is applied, the majority charge carriers contributes most of the current. This is why extrinsic semiconductors exhibit much higher electrical conductivity than the intrinsic semiconductors. One important point is that both electrons and holes always exist and both contributes to the electrical conductivity. That is the beauty of semiconductors. The the difference lies only in their relative concentration. In practical devices, controlling the flow of majority charge carriers and minority charge carriers allows engineers to design the switch, amplifier, logic circuit, and the communication systems. The modern electronics revolution is possible because we can manipulate the carrier moment with extraordinarily precision. Even every smartphone processor, memory chip, and communication device relies on these principles. Thus, the study of carrier transport is not merely theoretical, directly impacts the real world technology that billions of people are using every day. Session by comparing the intrinsic and extrinsic semiconductors. This comparison is extremely important because it summarizes everything we have learned about the semiconductor classification. First, intrinsic semiconductors are pure materials without any intentional impurities. Whereas the extrinsic semiconductors contains carefully controlled impurity atoms introduced through doping process. Second, in intrinsic semiconductors, the number of charge carriers, the number of electrons is always equal to the number of holes. In extrinsic semiconductors, the number of electrons is not equal to the number of holes. Either in p-type or n-type, either electrons are majority charge carriers or holes are majority charge carriers in n-type and p-type semiconductors respectively. Because Doping increases one type of charge carrier significantly. That depends on the doping type, either pentavalent or trivalent. The pentavalent impurity increases the number of electrons in n-type semiconductor, and the doping of trivalent impurity increases the number of holes, that is p-type semiconductor. Coming to the third point, the conductivity. The electrical conductivity in intrinsic semiconductors process relatively low, whereas in extrinsic semiconductors, which is much higher than the intrinsic semiconductors. It is because of the increased carrier concentration by doping process. The fourth point depends on the temperature. So as we already discussed at the beginning of the semiconductors are temperature dependent materials. Particularly in intrinsic semiconductors, the conductivity depends primarily on the temperature. The extrinsic conductivity depends on both temperature and doping concentration. Finally, in the practical applications, the intrinsic semiconductors are mainly used for understanding the fundamental semiconductor physics, whereas the external semiconductors are the materials actually used in electronic devices. This comparison makes the transition from the semiconductor fundamentals to the semiconductor devices. In the upcoming topics, we will see how the combined n-type and p-type semiconductors creates p-n junction diode, one of the most important electronic devices ever invented. The concepts you learned in these previous topics, from the fundamentals of semiconductors to the understanding of diodes, transistors, integrated circuits, and all modern electronic systems. This is how we can analyze and we can classify the semiconductor materials, and we can understand their properties, and we can find the desired applications based on the characteristics of the semiconductor used. Different semiconductors exhibits different properties. The electrical conductivity may vary from semiconductor to semiconductor because their band gaps are different, their electronic band structure is different. So different semiconductors exhibits different properties. Apart from this silicon and germanium, there are many compound semiconductors. Those compound semiconductors also under investigation in nanoscience and technology. So these semiconductors are playing a very crucial role in semiconductor device fabrication and the modern electronics and optoelectronic device fabrication and energy conversion systems like solar cells and all. the whole concept of semiconductors. Thank you very much, and I welcome you once again to the exciting learning journey in physics for engineers. Thank you.